So in class last time we talked about what the rate of reaction was and how to write a rate expression, which is the change in concentration over the change in time, and then the stoichiometry mattered. It can be written in terms of the disappearance of a reactant or the appearance of a product. Now we're going into section 14.2, which is going to go into rate laws and how the concentration of a reactant will affect the instantaneous initial rate of a reaction. So we're going to be writing rate laws here. So first of all, the rate law differs from a rate expression, although both of them are equal to a rate. Rate expressions give you the average rate over a certain given time in the experiment, whichever one you designate. It could be the first 100 seconds, it could be time 100 to 120 seconds, whatever ratio, whatever range of time, delta t, you want. Rate laws, in their hand, while they do the rate, this is going to be your initial rate at the moment the reaction starts. For that reason, rate laws can only be written in terms of reactants, because initially you don't have any product yet, so they're only in terms of the reactants. The other big difference between rate laws and rate expressions, the coefficients in the stoichiometry appeared in the rate expression. So if you had a coefficient of 2, your rate expression had 1/2 in the front. Here in rate laws, the stoichiometry does not affect the rate law at all. So the general way of writing a rate law, if I have a general reaction here, A plus B goes to C plus D, and whatever their stoichiometric coefficients are, the rate law is going to be equal to K, remember K is the rate law constant, times the concentration of your first reactant raised to some order, X, times the concentration of your second reactant, B, raised to some order, Y, where X and Y are determined experimentally. X and Y are not the coefficients. That is a common mistake, is to think that this X and Y must be your coefficients from the stoichiometry. The coefficients for the stoichiometry do not affect the rate law at all. You must determine what these coefficients are experimentally. X and Y are called the order of the reaction. These are the reaction orders, and you have to look at experimental data to determine them. The overall reaction order is going to be the sum of those exponents. So if I have, for example, say I have, this is our bromine and our formic acid from the last class. If we wrote the rate law for this and we have experimentally determined that it is first order with respect to the bromine and 0 order with respect to the formic acid, then overall your order is 1 plus 0, or first. So first order in respect to bromine, I should have a 2 there, bromine 2. 0th order with respect to the formic acid, and first order overall. But again, this first order to 0th order, those numbers had to have been determined experimentally. But the overall reaction order is just going to be the sum of them. So how do we determine this? So what does this mean anyways? These order of the reactions are telling us how directly does that concentration affect the rate of the reaction. If this is 0th order with respect to the formic acid, does that mean the formic acid had any effect on the rate? If the order is 0th, that means what? What's anything raised to the 0 power? 1, right? Which means this whole term goes to 1. So if that whole term goes to 1, does changing the concentration of formic acid change my rate? No. So that's what it means to be 0th order. That means that the concentration of that one reactant has no effect on the rate. Increasing its concentration won't speed up the reaction. Decreasing it won't slow down the reaction. Whereas first order means that these are directly proportional. First order, anything raised to the first order is just itself. So if I'm first order with respect to bromine, that means if I double the concentration, what happens to the rate? It doubles as well. Good. So that's what it means to be first order. It's a direct relationship. I double one, I double the other. I double the concentration, I double the rate. I half the concentration, it will half the rate. The relationship is direct. So that's what a first order means. So how do we determine these orders experimentally? We're on page 616 in chapter 14 here. And here is an example of a reaction. Fluorine, F2, plus 2 chlorine dioxides makes 2 FClO2s. Again, when we rate our rate law, it's only in terms of those two reactants, not in terms of the product, because this is our initial rate. So we have some rate constant K times the concentration of our first reactant, F2. Remember, the brackets mean concentration of. Raised to some order X, so this is the order with respect to fluorine, times the concentration of your second reactant raised to a different order here. So this is what we call the general format of the rate law. It means just looking at the equation, what do we know about the rate law? We know it has some constant K. We just don't know what it is yet. We know that we have two reactants and what they are, but we don't know what those orders are, so we leave them as X and Y. So this is our general rate law. To be able to determine what K, X, and Y are, we need to look at experimental data. So here we have some experimental data here. I've run this experiment 3 times, and in those 3 times I have changed the concentrations of my reactants and measured what my initial rate was. So in the first experiment, I have 0.1 molar fluorine and 0.01 molar chlorine. If I compare experiment 1 to experiment 3, then I doubled the concentration of fluorine while keeping the concentration of the chlorine dioxide the same. Why is that important? We want to only change one variable at a time. If we compared, say, experiment 1 to, experiment 2 to experiment 3, we've changed both the concentration of fluorine and the concentration of chlorine dioxide. That won't tell us which one caused the change in the rate, so we have to only change one variable at a time. So comparing experiment 1 to 3, we've doubled the concentration of fluorine while keeping the other variable constant. And what happened to my rate? It doubled. So I doubled the concentration, it doubled the rate. So what order is that? First order. Therefore, it is first order with respect to F2, so this is an understood 1. We just left it as that. So at this point in time, we know what the order with respect to X, or what fluorine is, what X is, but we still don't know what it is with respect to Y. So start over. Now, if I want to know what is Y, the order with respect to the chlorine dioxide, which 2 experiments would I compare? 1 to 2, because if I compared 1 to 2, now I'm keeping the other variable constant, but what did I do to the chlorine dioxide? Quadrupled it. What happened to my rate? It got quadrupled as well. So I quadrupled the concentration, it quadrupled the rate, so what is Y equal to? 1 as well. So it is first order with respect to both fluorine and chlorine. So now when we write our rate law, we know that X and Y are both 1. What's our overall order of the reaction? 2. Good. I'm first order with respect to both. The overall is the sum of the orders. So overall, second order. Now, looking at our rate law, what do we still not know in this rate law? What's still an unknown here? K. Okay, we don't know what K is. So, but we know that the rate is equal to K times the concentration of fluorine times the concentration of chlorine dioxide. At this point in time, we can solve by K by plugging in experimental data. Which experiment? Honestly, it does not matter. Experiment 1, 2, or 3, all of them should give you pretty close to the same K value. I always just pick the first experiment. So what that means is I'm going to take experiment 1 here, and I'm going to plug in its rate. So that's 1.2 times 10 to the negative 3. Molar per second equals K. And then I'm going to plug in what I have as the concentration of fluorine. So that's 0.1. molar. And what I have is the concentration for the chlorine dioxide, so that's 0.010 molar. Calculator for that one.
So if it was to 0, that would just be what?
That term would just go away. So say if it was the 0th power to chlorine dioxide, you would just have it just in terms of fluorine. One. So what are we getting here for K? $1.2. Good. What's our unit here going to be? Look at the units. All right, so I've got molarity per second on this side. On this side, I've got molarity, so that's going to cancel the molarity. When I divide this over, molarity is going to end up where? Top or bottom of the fraction? Bottom. So this is going to be 1 over molarity times second. And that's our value of K. 1.2, and the unit is 1 over molarity times second. The order of the reaction will determine the unit for K. And we'll see that in a little bit. Because if this was 0th order in the chlorine dioxide, we wouldn't have had that second term, and we would have only divided by molarity once. And that would have given us a different unit. A little bit muted in my handwriting there. Feel about that? We're good? All right. And let's try another example. Here we've got a theoretical reaction. A plus B goes to C plus D. If I asked you to write the general rate law, that's where we get rate is equal to K times the concentration of my first reactant raised to some X times the concentration of my second reactant raised to some Y. Again, whatever my coefficients are, A, little b, makes no effect on the rate law whatsoever. It doesn't appear at all. Here's my experimental results here. If I want to know what is X, the power with respect to A, I would, again, compare an experiment where I'm going to change the concentration of A while leaving the concentration of B unchanged. All right, so here, double the concentration of A, what happened to my rate? Double. So what's X? 1, right? Okay, so now what's the order with respect to B? Let's do. So which experiments am I going to compare? 1 and 3. Okay, so 1 and 3, A stayed the same. I doubled the concentration of B. What happened to my rate? Did it double? It quadrupled. So that would mean that Y is what? Not 1, but 2. That means that rather than it being a direct relationship, it's a squared relationship. If I double the rate, or double the concentration, my rate was quadrupled, or 2 squared. What would happen if I tripled my concentration? My rate would go up by a factor of what? If I tripled my concentration of B, what should happen therefore to my rate? It should go up by a factor of what? What's 3 raised to the second? 9. It would go up by a factor of 9, right? Okay. So it's first order with respect to A, second order with respect to B. Again, if I want to solve for K, I would just pick one of the experiments. We usually pick the first one just for consistency, plug in their concentrations and rate, and come up with a value for K. And then we can write our rate law with an actual value for K and values for X and Y, or orders of a reaction. Blech. What's the overall order of this reaction? 3. Good. This is a third order overall reaction. Notice that when we did this, we got a different unit for K, because here, down at the bottom, see, B is now squared. So when we plug in our concentration of B, we had to square it, because B is squared in our rate law. So when we square it, that doesn't just square the value, that also squares the unit. So I've got molarity canceled with molarity, but on the bottom, I'm still left with molarity squared. So molarity to the -2. Or if you prefer writing it that way, is 9.3 times, and then 1 over molarity squared times seconds. Same thing. Whether you prefer writing your units as a fraction or as negative powers, same thing. What happens if I did this, I changed the concentration of B, and my rate did not change? What would that mean? Y is. If I doubled the concentration of B, but my rate didn't change, what would that mean the power is? 0. Good. That means it didn't have an effect. So those are the 3 most common possibilities you'll see. Either changing the concentration will have no effect, in which case it's 0th order with respect to that reactant. It will have a direct effect, double one, the other one doubles, in which case it's 1st order, or it will have a squared effect, doubled one, the other one quadrupled. Whatever the change in your concentration is, square it, and that's what the change to your rate will be. How do you feel about that? Good. All right. So this table is on the bottom of page 617, and this talks about those, the overall reaction order, what the rate laws typically look like, and what the unit of your K will end up being. So 0th order. 0th order means that concentration of no reactants had any effect on the rate. So your rate law is just going to be the rate constant. Concentration of no reactants had any effect. 1st order, that means that your rate is equal to your 1st order with respect to one of the reactants, but not both. Or you only have one reactant, but to the 1st order. You end up with a K that is second to the -1, or 1 over seconds. 2nd order. 2nd order reaction means either you are second with respect to one of the reactants, or you are first with respect to 2 reactants for an overall 2nd order. Either way, your unit for K will end up being 1 over molarity times second. 3rd order means that you are usually second with respect to one of them and first with respect to the other. And as we just saw, you end up with units of 1 over molarity squared seconds. Which means that if I give you the value of K, including its units, can you tell me what the order of the reaction is? Can we make that jump? If I just told you you have a reaction that has a rate constant of 1.5, 1 over molarity times seconds, would you be able to tell what order the reaction is? If I said, let me write it up there. If I said you have some reaction with a rate constant that is 1.5, 1 over molarity times second, what is the order of that rate, or that reaction? 2nd order. Good, because 1 over molarity seconds is the unit for K for a 2nd order reaction. So that tells us this must be a 2nd order reaction. Why does it erase everything? Order reaction. Why am I pointing this out now? Because later on in this chapter, we'll get to word problems where it is important to know what your order of reaction is, because that will determine which formula you use to solve the problem. And I don't always write out for you right there in the problem, oh, this happens to be a 2nd order reaction. But I do give you K, so it's up to you to figure out what the order of the reaction is from K. If I don't spell it out for you right there in the problem what the order of the reaction is. because that will determine which kind of rate law you're going to use to solve the problem. So pointing that out now so we can make that jump later. All right, ready to try an example? This is just that. All right, so the gas phase reaction of nitric oxide with hydrogen at 1,280 degrees Celsius is given below. 2 nitrogen monoxides plus 2 hydrogens makes a nitrogen and 2 waters. From the following data collected at 1,280 degrees, that's images on the next slide, determine what the rate law is, the rate constant including its units, and what rate you would expect for the reaction given the following initial concentrations of the 2 reactants. So there is our experimental data, and we still have the equation up the front. So step 1, from that equation, our rate law is equal to what? Rate is equal to what? General order of the rate law. Rate is equal to what? Now, all the other rate laws, what comes before the concentrations? K, good. Lowercase k. There's our rate law constant. What's next? Just NO or in brackets? Brackets. What do the brackets mean? Good. Concentration of NO. What's the power going to be? X. We don't know it yet. Then what? Good. Raised to what power? Y. Good. So there's the general format of our rate law. So to find what X is, what 2 experiments am I going to compare? 1 to 2, good, because 1 to 2, I didn't change what hydrogen is, but I did what with the nitrogen monoxide? Be careful with scientific notation. 5 times 10 to the negative 3 versus 1 times 10 to the negative 2. What happened? Let's write it out of scientific notation. 5 times 10 to the negative 3 is 0 point how many zeros? 2 zeros, 0, 0, 5. Versus 1 times 10 to the negative 2 is 0 point what? 0, 1. What happened? Doubled, right? 0.005 to 0.01, that was doubled. That was doubled. Scientific notation confuses you, just take it out of scientific notation. Looking at our rates, what happened when we doubled it? If you're not sure, because that doesn't look like it just doubled, let's take the second number and divide it by the first number. So 5.0 times 10 to the negative 5th divided by 1.3 times 10 to the negative 5th. What does that give us? .85, which is pretty close to what whole number? 4. So it's approximately 4. So when we doubled it, we approximately did what to our rate? Quadrupled it, which means what is x? 2. Good. X is 2. Now try and figure out y. Getting loud out there. What's y? Why?
Because if you compare 2 and 3,
Mm-hmm.
those have the same concentration for nitrogen oxide.
Good.
It doubles for the hydrogen from 2 to 1 times 10 to the negative 3 to 4 times 10 to the negative 3. And then from the initial rate doubles as well.
Good. This doubled. And this doubled. If you're not sure if that doubled, pull it out of scientific notation again. You'll find the same thing. It actually does double.
So what if you were to look at the other one, from 1 to 3?
1 to 3 would not be a good comparison because you would be changing both the concentration of hydrogen and nitrogen monoxide. So y is 1. So now how do we find the value of K? Plug in the numbers. Doesn't matter which one. Let's just pick experiment 1. So the rate for experiment 1 was 1.3 times 10 to the negative 5th molar per second equals, K is what we're solving for. Concentration of NO in experiment 1 was 5.0 times 10 to the negative 3rd molar, and that is squared. Don't forget to square it. X was 2, so square that. Times the concentration of hydrogen raised to the first power, so hydrogen was 2.0 times 10 to the negative 3rd molar.
I'm at 260.
260, good. 260. And what is our unit here going to be? Molarity, not meters. Molarity to the negative 2 times seconds to the negative 1. Good. What's your overall order of that reaction? 3. So if you're not sure about the unit and you're iffy about your math, double check that handy little table right there. Third order, molarity to the negative 2, second to the negative 1. That will also tell you if you did it right. So there's our value for K and its units. So last one, C, asks us to determine what is the rate of the reaction at these following concentrations. So now that we have our complete rate law, let's write it out. Rate is equal to, we now know K is 260 molar to the negative 1, or sorry, negative 2 seconds to the negative 1, times the concentration of the nitrogen monoxide, we know is a second order, and the concentration of hydrogen we know is a first order. So there's our new rate law. Find what the rate is at these two new concentrations, which means just plug in those concentrations. What do we get for our new initial rate? I'm getting 3.7. Did you square the 4.8? Don't forget to square your concentration of nitrogen monoxide. All right, I'm getting 3.7 times 10 to the negative fifth. Anybody get something different? And what will be our unit here? Good, molarity per second. Because molarity squared will cancel with molarity to the negative 2. So we're just left with molarity, bring the seconds to the negative 1. So molarity per second. Yep. Ta-da. How do we feel about writing rate laws, determining the order of the reaction, determining K, and using your new rate law to determine a new rate? So this section is called the dependence of the reaction rate on reactant concentrations. So this is what you do when you're changing the concentration of the reactants. All right. Next, we're going to look at those reaction rates and see what happens over time to the reaction. So we saw before that as time goes on, what happened to the rate of the reaction? Did it speed up, slow down, or stay constant? It slowed down. Good. Those reactant molecules got further apart because there were fewer of them, more of them were used up, and the reaction overall slowed down. But that was just qualitative. Now we're going to quantify that. And we're going to look at it for just first order and second order reactions. So for this section, we're not going to worry about the 0th order reactions because they're not dependent on anything anyways. And we're not going to worry about the third order reactions because the math with them gets really complicated really fast. So we're just going to deal with first order or second order reactants. And we're going to simplify it further. And when we talk about second order reactions, we're just going to worry about second order reactions with one reactant raised to the second order. So just to simplify our math, because this is about to be calculus. Don't worry, you don't have to do the calculus, but that's where these numbers come from. All right, so if I have a simple reaction, A is our reactant, it goes to some products. Doesn't really matter what the products are because they don't affect the rate law. We know that now. If I were to write the rate expression in terms of A, rate is equal to negative, because it's a reactant, it's being consumed, change in concentration A over change in time. If I were to write the rate law, then the rate is equal to K, our rate constant, times A. This is for a first order reaction, so raised to the first power. These are both equal to the rate, so I can set them both equal to each other. The thing is, this is only equal to the initial rate. So the initial rate is at time what? Time 0. All right. So if this denominator, the change in time, is going all the way down to 0, and we're dividing by a smaller and smaller number, what we're doing here is taking an integral. So we're integrating this with respect to time. So that's why it says applying calculus. Again, you guys don't have to do the calculus. This is just where the formula came from. So our final equation here, and this is equation 14.3 on page 620. This is what we call the integrated rate law for a first order reaction. Integrated. Let's keep doing that. For a first order reaction. So, natural log of your concentration at some time t. divided by the natural log of your concentration initially, or at time 0, is equal to negative K, your rate law constant, times T, whatever your time is. What this allows us to do is it allows us to calculate what our concentration should be at any given time. So if I want to know if I know what my rate law constant is, and I know what my initial concentration is, and I want to know, okay, what should the concentration be after 5 minutes? I can apply this rate law and determine what my new concentration is. So this is the law you use where instead of changing the concentrations, you're asking for what is the new concentration at a time, or flip it around, how long will it take to reach this lower concentration? That's when you use the integrated rate law. So let's look at an example of this one. So we're on page 621, looking at sample problem 14.4. Here's the decomposition of hydrogen peroxide. So hydrogen peroxide, you put it cleaning something up, or you put it on a scrape and it bubbles up, and those bubbles are oxygen gas, and what's left over is plain old water. Decomposition of hydrogen peroxide. The rate constant for this reaction at 20 degrees Celsius is 1.8 times 10 to the negative 5th reciprocal seconds. So that is my K right there. The rate law constant, there's K. If the starting concentration of hydrogen peroxide is 0.75 molar, so that is starting concentration, H2O2 at time 0, determine A, the concentration remaining after 3 hours, and B, how long will it take for the H2O2 concentration to drop to 0.1 molar. I'm going to get a blank page so I have more space. All right. So, first of all, we're in part A, asked what is the concentration remaining after 3 hours? So we're asking what changes when over time. As soon as you're looking at a time factor, is one of your variables being time, you know you're using the integrated rate law. We also know that this is a first order reaction. How do we know it's first order? Because what? Good. The units of the rate law constant are reciprocal seconds. The other thing is in this problem it told you it was first order. It told you it was first order, but I might not always be that nice. Hint. So it told you it was first order, but if I hadn't told you that from the units of K, you would be able to tell it's first order, because that will determine which rate law you use. So the integrated rate law for the first order reaction is right here, the natural log concentration of T over the concentration at time 0 equals negative KT. So I'm going to write that over here. Natural log concentration of A at times T for A initially is equal to negative KT. So in question A, what am I solving for? What am I being asked to find from my rate law? Which one? The top concentration. The concentration remaining after some time T. So we're going to have to get rid of that natural log. That's okay. It's just like the Clausius-Clapeyron equation in chapter 13, right? Okay, so how do we get rid of the natural log? E to both sides. All right, so E and natural log will cancel. We get concentration of A at time T divided by concentration of A initially is equal to E to the negative KT. Bring A to the other side. A at time T is equal to E to the negative KT times, on the outside of E, concentration of A initial. Careful, that's on the outside. That is not inside the power of the exponent. That is on the outside. So looking back to our problem, what is the value of k? Good. 1.8 times 10 to the negative fifth, reciprocal seconds. What is t, our time, going to be for part A? Yes, why? Good. So we're given 3 hours. We're given 3 hours, but why do we need that in seconds? Good, because k is in reciprocal seconds, and we have k times t. Can you have a power inside of an exponent? Is that allowed in math? No, math does not allow you to have a power inside of an exponent. So we need to get rid of that, or sorry, power. You cannot have a unit inside of a power of an exponent. Okay. Woo. You have to get rid of that unit before you can take the power of e to it. So k and t must cancel out each other's units, which means we need to take these 3 hours and turn them into seconds. How do we do that? Divide by 60? Multiply by 60 times 60, or times 60 squared. 3,600 seconds per hour. So that's however many seconds that is. 1,800. Sounds right. Ooh, seconds. All right. Last thing we need to know what A naught or A0 is. What was our initial concentration of our reactant? Good, 0.75 molar. All that's left now is plug them all into our little rate law up here. So e to the negative. Probably going to regret writing it up here because I'm going to run out of space. Fifth, 3 seconds to the negative 1. And then times 0.75 molar. Because our units inside of the power cancel, the only unit we're left with is the molarity on the 0.75 down here. 7 looks like a 3 for some reason. Molar. Now, should our concentration go up or down? Down. This is a reactant, so its concentration should go down. So that's another way you're making sure you're on track. Your concentration should decrease. So we should get something number smaller than 0.75. If your number went up, most likely what happened is you forgot the negative in front of your exponent there. This isn't a very fast reaction. It shouldn't go down a whole lot. What do we get? Good. 0.62, and what's our unit here? M, molarity. So that is our concentration after 3 hours. Again, if you don't like the algebra of getting rid of natural logs, just go ahead and have it rewritten in this format here, solved for the concentration at time t. Have that on an equation sheet that you can easily refer to during your homework and on tests that says, here is how to find the concentration of a first order reaction after some time t. Make things easier for yourself. Little bit of planning will go a long way towards making things easier. Any questions about that? So, what do you think we're going to do next? What? No, not yet. This was the integrated rate law for first order reaction. Second order reaction. Okay, let's look at the second order reaction. All right. Oh, wait. There was a second part, wasn't there? The second part, part B, was asking you how long will it take. So in that case, which term are you solving for? T. We don't think we really need to do that one. That one's just solving for T. That one's even easier because you don't have to get rid of the natural log. Solving for T. Just plug in the two concentrations, solve for T. Not bad, right? All right, second order reactions. This is just talking about another way of determining whether or not your first order reaction or second order reaction is to graph the concentration over time. If you look at the integrated rate law for a first order reaction, natural log of concentration of A over concentration of T. All right, see how many of you guys have had Algebra 2 trig. Natural log of a fraction is the same thing as natural log. So if I have natural log of x over y, that can also be written as what? Perfect. Natural log x minus natural log of y. So that's what they've done here, is they've taken the natural log of AT and natural log of A initial and then brought the natural log of A initial over the other side. So that's what they did here. So natural log of A in time t is equal to that negative k times t plus the natural log of A. What is our independent variable here? Is it time or concentration? What's the independent variable? Oh, back to chapter 1. Independent variable versus dependent variable. Time. Good. Time is the independent variable. Time's going to keep on going no matter what. It doesn't depend on anything else. Concentration is the dependent variable. That depends on how much time has passed, right? So if time is our independent variable, if I am doing a graph, that goes on which axis? Y or Z or X? X. So t, our time, is x. If y equals mx plus b, that is the equation for a what? A line. That means that negative k is m. What is m? Slope. So slope is equal to negative k. Natural log of concentration initial is equal to b. What is b? Y-intercept. And our y value is going to be the natural log of A. This should give us a straight line. In other words, if I were to graph the natural log of my concentration versus time, I should get a straight line. So here is for a first order reaction. If I just straight up put concentration versus time, I don't get a straight line. That's a hint that it's not zero order. By the way, didn't show it here, but a zero order reaction, it would be a straight line if you just graph the concentration versus time. But if I take the natural log of my y-axis here, this is part of the lab you were supposed to do today, but didn't get a chance to. Natural log of A over versus time, now we get a straight line. So this is another way of experimentally determining if you were first order or second order, is by graphing it and seeing what will give you a straight line. So that was on the top of page 622. All right. Let's try. That's kind of an involved question, and we're kind of getting short on time, but I want to make sure we get. Yeah, we'll just do this one quickly, not go through every single step. The rate of decomposition of azomethane is studied by monitoring the partial pressure of the reactant as a function of time. So we learned last time that when you're dealing with gases, the pressure change and the concentrations change are going to be directly proportional. They're just off by a factor of 1 over RT, which came from the ideal gas law. But when you're just comparing, you can still use the pressures as concentrations when you're doing these rate laws. Here's the following data that's obtained at 300 degrees Celsius. As time goes on, here are my pressures. So time goes on, here's your pressures. And this example is on page 622. Determine what is the rate constant of this reaction. Determine what is the rate constant. Now, I can't determine the rate constant using the method that we used last time because that gave us rates as we changed the concentration. Here I'm given time and pressures. So if I'm dealing with time, that means I'm dealing with integrated rate laws. So now we're going to determine graphically whether or not it's first order versus 0th or second order. So if it's first order, will graphing the time versus the pressure give me a straight line? If it's first order, will graphing time directly versus pressure give me a straight line? No. For a first order reaction, what do we have to graph to get a straight line? The time versus the what? Natural log. Okay. So first thing we're going to do is we're going to take these pressures, because again, pressures and concentrations, they're going to be the same as far as rate laws, and we're going to take the natural log of all these numbers. So we're going to make a new table, still time, but now the natural log of the pressures. We graph that, sure enough, we get a straight line. So this is why this isn't a good example for you guys to be working on in class, because you don't have, well, you might if you have a graphing calculator in front of you or a laptop, but you don't have graphing software right now to do this one. I would not ask you to do this one on a test unless I provided you the graph paper, so don't worry about that. So we got a straight line. So from this straight line, how do you determine what the rate constant K is? It's the slope, right? The rate constant is the slope. So how do you find the slope of a line? Rise over run. Or if you're using graphing software, the graphing software should be able to calculate the slope for you. So in this case, we were, did they do, yeah, they just did they use rise over run? Yeah, I think they used rise over run. Yeah, they did slope as a rise over run, and they did it from 250 to 100. Or you can use graphing software to tell you what the slope was.
So we're not going to get that.
No, because I'm not going to require you to have a graphing calculator.
Is there anything you need to know?
You might see it on a LearnSmart, but what you would need to know on a test is the graph would already be given for you, the slope would already be given for you. I might ask you what is the order of the reaction, what is K, but I would already have the math up for you. It would just be up to you to go, oh, K is the slope, and I'm told the slope is this number. Yeah. But I would go ahead and do the math for you. I would just tell you, if you graphed natural log of pressure versus time, you end up with this straight line. Here's the equation for the line. And it would be up to you to go, oh, well, I'm looking for K. K is the slope. So the slope of that line. But the slope would already be calculated for you. It would just be in the equation. Yeah. For this, I'm more interested in the concepts than can you graph this stuff. All right. One more concept about first-order reactions before we move on to second-order reactions. That is called the half-life. Where do you hear the term half-life thrown around a lot? Biology, right? What are we using in biology for? Half-life. Don't know, but we hear about it.
I forgot.
What else? What? Radiation, right? The half-life of radiation, or things like radiocarbon dating. What is radiocarbon dating? How old something is. Something really old. We measure the amount of carbon-14 in it, right? C14 dating is radiocarbon dating. And we talk about the half-life of radioactive isotopes, whether it's a really long isotope, such as carbon-14 to measure something really old, or something that we hope has a really short half-life, like, say, a radioactive isotope of iodine that you're using for a medical application. You don't want that to have a long half-life, because that means that your patient will be radioactive for a long time. So if we're using a radioactive isotope for medical reasons, we want them to have short half-lives, so they're gone. The person isn't walking around radioactive for the rest of their life. All right, so half-life. Half-life is defined as the amount of time it takes for half of your reactant to be gone. So in the case of an isotope, that means how long it takes for half of that isotope to decompose. In the case of a chemical reaction, we can still have a half-life. It's just a chemical reaction instead of, in the case of a radioactive isotope, it was a nuclear reaction here. So if we take our integrated rate law and we say, okay, half of our reactant is gone, then that means that whatever our initial concentration A initial is here, our final concentration at T is going to be half of that. So A initial, or AT, is going to be 1/2 of whatever your A initial is. So I'm going to plug that in. AT, right here, is 1/2 of A initial. What's going to happen to our A initials here? I've got A initial at the top and the bottom. They're going to cancel out. All right. So we're just left with the natural log of what here? A half is on the bottom of the denominator, so natural log of not a half, but dividing by a fraction is the same thing as multiplying by its reciprocal. So what's the reciprocal of 1/2? 2. Okay. So what's the natural log of 2? Somebody plug in their calculator. What's the natural log of 2? Yeah, probably could guess. Natural log of 2 is 0.693. So we can rewrite that the half-life is equal to 0.693 over K. Yep, that is our final equation. Yep. That equation is on page 624, equation 14.5. And this is the half-life of a first-order reaction. So it will not work for a second order, in other words. Half-life of the first-order reaction. Now that 0.693, is it always 0.693 for a first-order reaction? Yes. Yes, it is. So that number is constant. And that is from the natural log of 2. That number is the same. All right. Let's try the super hard problem here. The decomposition of ethane, C2H6, to methyl radicals is a first-order reaction with a rate constant of 5.36 times 10 to the negative fourth reciprocal seconds at 700 degrees Celsius. Calculate the half-life of the reaction in minutes. And they've given you that 60 seconds are in a minute in case you didn't know that one. Just give you a leg up here. So what's our equation of half-life? Half-life is equal to? For this problem, what is our K? And what's the unit on K? Inverse of second. Good. Inverse of seconds. Whew. So 1293. What's my unit now? Seconds. Good. 1 over seconds inverse just becomes seconds. But I want it in minutes, so what do I need to do with this number? Yay, divide by 60. So how many minutes is that? 21 and a half minutes. Okay, that one was hard. I was sarcastic. So finding the half-life of a first-order reaction, not so bad. Do not panic over that question, which is why it's helpful, again, to have an equation sheet where you have written, this is the half-life of a first-order reaction. I could also have flipped this around and said, if the half-life of this reaction is 21.5 minutes, what is the rate law constant? And you could have just been solving for K.
Is that going to be in the homework for practice?
My homework questions, I only gave you 10 questions, so I kind of had to pick and choose. I can't remember off the top of my head which examples I gave you and which didn't. But there's more questions on the Learn Smart, and of course, there's plenty of practice problems in the test, and the homework are in the textbook. So,
In the textbook, is there one rehearsed?
I think so. Yes, do on page 625, practice problem B. It says calculate the rate constant for the first order decay given that the half-life is 14.7 hours.
Page
Yeah, page 625.